Only twice before has an object from deep space slingshotted through our solar system, and now 3i Atlas has arrived. It's fast, old, and acting just strange enough to set off a global observing frenzy and a million online theories. In this video, we'll ask a simple question with very big implications. Are we witnessing a genuine black swan, rare, high impact, and only explainable after the fact? Or just the most dramatic example yet of something astronomers always knew was coming? Think of a black swan as a stress test for your understanding of the world. It isn't just something surprising, it's an event that embarrasses our predictions. 3 ingredients make it a black swan. First, you don't reasonably expect it beforehand. Second, when it happens, it hits hard. In money, in models, in meaning. Third, after it happens, people knit a neat little story that makes it look obvious in retrospect. That last part is the trap. The smoother the explanation after the fact, the more likely you're looking at a true black swan rather than a routine surprise. So before we ask whether 3i Atlas qualifies, let's get really clear on the mechanics of rare, impact, and retrospective storytelling, and how those ideas translate from financial markets and pandemics to the quiet mathematics of the night sky. Start with rarity. In astronomy, rare is slippery because the universe is large, patient, and constantly rolling the dice. An event can be astronomically unlikely at any given moment, yet practically guaranteed over long time scales. So the right question isn't, is this weird? It's, what was the reasonable prior expectation that we would see this, here, now, with the instruments and surveys we actually have? Rarity is observer relative. Before wide-field automated surveys, an interstellar visitor could cruise through and we'd simply miss it. That doesn't make the universe different, it just means our sampling was poor. As telescopes improved, our priors updated. The class of events we call discoverable expanded. In Taleb's language, if your sampling process blinds you to tail events, those tails will feel like miracles. Improve your sampling, and miracles become data points. Now, impact. People often picture impact as physical damage. A rock hits Earth. Cue the dinosaur documentary. But impact has 2 distinct faces. There's physical impact, energy, collisions, disruptions, and there's epistemic impact. How much the event forces us to rewrite our models, reallocate budgets, and redraw the map of what's plausible. Epistemic impact matters just as much. If a single discovery reshapes instrument priorities, sparks a dozen new grant calls, and alters the assumptions in our textbooks, it's high impact even if no city has to duck for cover. Space is mostly about the second kind of impact. A new kind of object, a new kind of chemistry, a trajectory we hadn't modelled, or a brightness behaviour that breaks the rules. These can be seismic for science, because they relocate the centre of gravity of our expectations. Finally, the retrospective storyline. Humans hate blank spaces on maps, so we invent bridges between dots. That's the narrative fallacy. Once an event occurs, we compose a tidy explanation and, in doing so, backdate our confidence. Of course this happened, we say. All the signs were there. In reality, the signs are not there until the event gives them meaning. In astronomy, this often looks like a post hoc chain. Well, given the number of protoplanetary disks and the ejection of planetesimals, and the sensitivity of Survey X, naturally we were bound to see object Y by year Z. That may be reasonable science as a sanity check. It's not the same thing as an ex-ante prediction your reputation or budget depended on. The difference between post hoc coherence and foreknowledge is the heart of the black swan test. With those 3 pieces in place, we can map the concept onto a visiting interstellar comet. Before the first such detection, most people outside small specialist circles would have assigned near 0 to the chance of seeing one in their lifetime. Insiders, meanwhile, knew the physics allowed it, but had no strong expectation about when. After the first 2 detections, a subtle shift happened. Rarity decreased in a practical sense because our instruments, surveys and search habits adjusted. That adjustment matters. A phenomenon can remain rare in cosmic terms while becoming routine for a surveillance system tuned to catch it. Black swans often evaporate under better measurement. You don't make the universe less strange, you make yourself less surprised. But don't rush the verdict. Black swan status isn't a badge you pin on a raw category, interstellar visitor. It emerges from the specific details. Move any of these sliders and the classification shifts. The prior, what did reasonable observers expect given the data available before the event? If the professional consensus was plausible sometime this decade, the rare criterion is weaker than if the consensus was not in our working lifetime. The magnitude. What is the measured or modelled impact? Physical or epistemic? A faint, ordinary chemistry teaches us something, but not at a civilization-shifting scale. An object with exotic ices, unexpected outgassing, or a gravitationally puzzling path could move funding streams, mission targets, and theories. The story trap. Are we watching people knit a clean explanation only after seeing the data? If the community can point to dated, pre-event analyses making testable predictions that match the outcome, that's not a narrative fallacy, that's foresight. If the confidence arrives only after the discovery, caution lights should flash. There's also a useful gradient to keep in mind: white swan, grey swan, black swan. A white swan is expected and fits the model. A grey swan is rare but anticipated at low frequencies. You wouldn't be shocked, you'd just be impressed. A black swan blindsides not just the public, but also the prepared. Where a given interstellar object sits on that gradient depends on its behaviour. A pedestrian-like curve and conventional coma chemistry across familiar temperature ranges. Grey A, dramatic non-gravitational acceleration with no dust to blame, or a composition that doesn't match known condensation sequences, you're shading darker. A related idea from Taleb's broader framework helps here: fragility versus anti-fragility. A fragile system is harmed by variability, an anti-fragile one benefits from it. Science, at its best, is anti-fragile to anomalies. Each outlier is a gift. Institutions, budgets, public trust, and mission timelines, however, can be fragile. A true black swan exposes those fracture lines: sudden reprioritization, scramble planning, controversy, and heated debates about what to build next. If an event forces us to rethink risk models for planetary defense, or yanks big missions toward new targets, the system's response tells you something about the event's impact in Taleb's second sense. Let's also talk about reference classes, because choosing them wrongly is how people accidentally manufacture or dismiss black swans. If you compare 3i Atlas to all comets ever, you'll overstate the surprise. Interstellar visitors are a different class from solar-born comets. If you compare it to interstellar objects that are both detectable and actively searched for by modern surveys, you may understate the surprise, because that class is small and biased by recent capability. Honest analysis toggles between multiple reference classes to see how sensitive your conclusion is to your framing. If the black swan verdict flips just because you change the denominator, your verdict is fragile. There's also the problem of fat tails. In fat-tailed worlds, the improbable isn't as improbable as our intuition says. Extremes dominate averages. The cosmos is famously fat-tailed. One big supernova outshines millions of quiet stars. One well-timed discovery can outweigh years of null results. In these regimes, the right strategy is not predict the exact rare event, but build processes that harvest value when any rare event appears. That means global coordination of telescopes, flexible scheduling, rapid response pipelines, and a culture that treats anomalies as opportunities rather than embarrassments. If you have that posture, you stop asking, will we see a black swan? And start asking, are we positioned to benefit when one swoops in? We should also face the meta question: how much of black swan talk is performance? The label can be misused to inflate drama. A good stress test is to ask, what would have counted as a clear-cut falsifier of your expectations before the event occurred? If you can name concrete thresholds, brightness beyond X at distance Y, spectroscopy showing Z, a trajectory implying W, then you are operating with real, risky predictions. If, after the fact, every possible outcome can be explained as consistent with expectations, you weren't making predictions, you were reciting truisms. Black Swan thinking punishes that kind of vagueness. And then there's the role of time. The Black Swan label isn't frozen the day an event appears. As follow-up data accumulate, what looked shocking may settle into a familiar pattern, or what looked ordinary may sprout anomalies under closer inspection. Early takes are usually wrong in direction and magnitude. A sober approach leaves room for two updates, one as the light curve and spectra mature, and another once the community's institutional response becomes clear. Grant calls, telescope time, emission proposals, public narratives. Sometimes the science is modest, but the social impact is large, sometimes the opposite. Both count. So what practically would make 3i Atlas feel like a true black swan rather than a rare but expected messenger? Before discovery, if the serious dated literature had converged on we will likely not see such an object with our current survey footprint for many decades, that would satisfy the rarity criterion. If the object then delivered outsized consequences, say, decisive evidence for an alien condensation environment that disrupts planetary formation models, or instrumental retargets that ripple through major agencies, that ticks the impact box. And if, right after, you hear slick stories feigning inevitability, while the actual pre-event record was ambivalent or pessimistic, that's the narrative tailwind of a black swan. Conversely, if baseline expectations already allowed one or a few such detections within this time frame, and the data mostly refine existing theories, then what we have is closer to a grey swan, statistically rare, culturally exciting, scientifically valuable, but not a genuine wound to our sense of what's possible. One last guardrail: humility. The cosmos doesn't owe us tidy categories. It is entirely consistent to say, we don't yet know, and to let the label float until the evidence hardens. Black Swan thinking isn't about melodrama, it's about intellectual posture, keeping priors honest, resisting the seduction of hindsight, and designing systems that gain from uncertainty. If we hold that posture, 3i Atlas, whatever else it turns out to be, becomes more than a story about a strange traveller. It becomes a mirror for how we deal with surprise itself, whether we break, whether we bend, or whether we learn to benefit from the very shocks we never saw coming. Imagine meeting a traveller who doesn't share our family name. Most comets are distant cousins from the sun's own far-flung suburbs, the Oort cloud or the Kuiper belt, nudged inward by gravity and sunlight until they flare, shed, and loop back home. An interstellar comet is different. It was born under a completely different star, sculpted by a different nursery of dust and gas, then exiled by the gravitational drama of that system until it wandered the dark between suns. When such a traveller drifts into our neighbourhood, we're not just seeing another icy body, we're reading a postcard from another planetary childhood. That's what makes 3i Atlas so compelling. It isn't a regular in our family album. It's a guest with unfamiliar bones. Its ices, dust, and subtle colour can hint at chemical recipes our sun never used. And because this is the third confirmed visitor of its kind, the story shifts from one-off miracle to emerging class. The first time we argued over what it meant. The second time we realised it wasn't a fluke. With 3i Atlas, patterns begin to appear. How bright such visitors tend to be, how they behave near sunlight, how often we can expect them, and what they might tell us about the chaos of planet formation everywhere else. In other words, the object itself is data, but the fact of its visit is also data. It tightens our estimates of how frequently other solar systems eject debris, how much of that debris is icy rather than rocky, and how visible those exiles become when they graze a star's warmth. Even the feel of the coma, the diffuse atmosphere a comet grows when it warms, becomes a laboratory. If the gases peel off at different rates than we expect, it can mean unusual mixtures or grains that cling and release in odd ways. You can think of the glow around 3i Atlas as a whisper of its birthplace. We listen not just for volume, but for accent. The way a discovery like this happens is part detective story, part factory. Surveys such as Atlas patrol the sky the way a lighthouse sweeps the sea, not once, not twice, but continuously, looking for pinpricks that move when stars don't. Each exposure is a still frame. Stack enough stills and a moving dot draws a line. That line is a clue. At first, 3i Atlas would have looked like any other dim, stubborn pixel. No tail, no drama, just a dot marching against the backdrop. Software flagged it as interesting. Human eyes checked the habit of its motion. Too fast for a distant galaxy, too smooth for noise, too coherent to be a satellite fluke. Then comes the chain reaction. Observatories around the world take follow-up images to lengthen the track. With more track, you get a better sense of the path. Very early on, astronomers ask a blunt question. Is this bound to the Sun or not? If it's bound, it belongs to us. It will loop in an ellipse and someday return. If it's not, it's a passerby on a one-and-done curve, paying the toll of sunlight before racing back to interstellar space. That verdict doesn't come from a single snapshot. It comes from nights of measurements stitched together, each one shrinking the uncertainty. Along the way, little peculiarities reveal themselves. Maybe the dot brightens slightly from one night to the next, early hints of a coma. Maybe there's a smear that refuses to be a star, a faint tail betraying dust pushed outward. The world's coordination is the quiet miracle here. Someone in one hemisphere catches a low-altitude glimpse before dawn, another team in a different time zone grabs it after dusk. A handful of amateurs thread tiny telescopes through the gaps in the clouds to fill in the timing. All those photons land on sensors, and by the time morning coffee's poured, the small army of orbit calculators has turned those smudges into a preliminary path. That's when the messages start. Looks unbound. Activity suspected. Request more observations tonight. The machine of discovery hums, powered by shared curiosity and a little insomnia. Once the path settles, the geometry paints the drama. 3i Atlas is on what you can imagine as a deep, swooping arc that doesn't close. A visiting road, not a racetrack. The sun tugs on everything, of course, but there's a threshold between held and free, and this traveller crossed that threshold long before it met us. It will lean toward the sun, swing through its closest approach, and then climb away, never to be seen again from earthly eyes. That single pass defines a compressed story, an inbound chapter when it's still cold and mostly quiet, a fevered middle when the sunlight stirs buried ices and jets wake like geysers, and a fading epilogue when the heat falls off and the coma thins back into silence. Timing is merciless. If the closest approach to the sun happens when the object is near the sun's glare from our point of view, observers on Earth get a frustrating trade. The most interesting physics occurs precisely when seeing it is hardest. That's why the choreography of telescopes matters. Some telescopes catch the before and after, others try risky observations in twilight, and spacecraft, if we're lucky, snag views from vantage points far from Earth's line of sight. Throughout, the path isn't perfectly smooth. Outgassing acts like a garden hose in slow motion. Material streaming off the surface gives the nucleus tiny pushes that add up. Those pushes won't turn a goodbye into a capture, but they can shift the angle of the exit ramp, alter the spin, and change how dust grains spread into the tail. Watching those shifts tells us about the engine under the hood, which ices sublimate first, how vents open and close, whether the crust is crumbly or stubborn, and then there's the cosmic etiquette of close encounters. Planets add their own tugs. Most of the time, those tugs are small nudges, but they can still sculpt the shape of the coma from our perspective, adjusting what we can see and when. The punchline is simple, even if the dance is not. 3i Atlas is a messenger passing through. It won't settle down, it won't loop back for a second act, and it won't politely wait for better weather. We either build our observing plans to catch it on this one swing, or we miss the chance and accept that interstellar space has reclaimed its wanderer. And looming over all of this is the meaning of the third time. The first interstellar object taught us shock. The second taught us humility. 3i Atlas teaches us tempo. It suggests that our sky, when watched with enough patience and automation, is threaded by visitors more often than our grandparents would have guessed. That realization changes how we schedule telescope time, how we design alert systems that ping observers within minutes, and how we prepare analysis pipelines that can turn raw images into physical insight before the moment is gone. The voyage of 3i Atlas is a test of our readiness as much as it is a phenomenon in itself. Can we measure the chemistry of a worldlet made under a foreign sun? Can we track the subtle jets that stir it? Can we trace its one-pass curve with enough finesse to reconstruct the invisible hands that shaped it? We won't get a second try. That's the thrill and the sting of an interstellar encounter. It gifts us a laboratory we cannot keep and a deadline we cannot move. How big is 3i Atlas, really? If you've ever tried to judge the size of a firefly from the glow alone, you already know the problem. For comets, the glow, the coma and dust, swamps the solid heart, so brightness is a slippery proxy for size. Early ground-based analyses and pre-covery images hinted it could be multi-kilometre across, with some popular write-ups floating numbers in the single-digit to low two-digit kilometre range. But sharper eyes brought humility. Hubble's first close look didn't resolve the nucleus directly, yet it narrowed the possibilities, placing a firm upper limit around a few kilometres wide and allowing that the core could be smaller than a kilometre. In other words, we don't see the pebble, we see its fog. The safer takeaway is a range, not a headline number. For scripting purposes, think small city block to small town, not continent breaker, with the final call dependent on how reflective the surface is and how much of the brightness is just dust and gas. Why the widespread? Because turning glow into diameter is a chain of assumptions. You guess how shiny the surface might be. You estimate how much dust is floating in the coma. You model how sunlight and viewing geometry inflate the apparent size. You subtract, correct, and still live with uncertainty. Even Hubble can't peel the fog cleanly at this distance. The nucleus is embedded in its own atmosphere. That's why teams lean on multiple instruments and wavelengths, from visible light images to infrared spectra, each tugging at a different thread of the problem. The cross-checks are already paying off. As constraints on the coma and its dust production tighten, the allowed window for the nucleus shrinks with them. Size isn't just trivia, it changes the story you tell your audience. A larger nucleus stores more volatile ices, keeps activity going longer, and shrugs off some of the stress of solar heating. A smaller one can still put on a show if its ices are shallow and the surface is crack-prone, but it's likelier to sputter, fragment, or fade faster after its hot lap around the sun. Chemistry complicates this further. 3i Atlas is unusually rich in carbon dioxide compared with water, a mix that can drive strong activity even far from the sun where water ice would normally stay quiet. Add in the first unambiguous detections of water outgassing, and you've got a nucleus that can punch above its weight brightness-wise, without being especially huge. That's another reason raw glow can mislead you about bulk. When we talk about age, we're really asking, how long has this traveller been in the deep freeze between stars, and what kind of childhood did it have before exile? Trajectory modelling and its blistering speed tell a simple tale. This object doesn't belong to our sun, and has likely been wandering for many billions of years. Some analyses even suggest it could predate our solar system by several billion years, meaning it formed around a star that lived and died or simply moved on, long before Earth was a glimmer in a protoplanetary disk. That's not romance. It's the logic of interstellar ejection plus the chemistry we're starting to read in its coma. Old ice carries old stories. Age shows up in the ingredients list. With James Webb's infrared vision, 3i Atlas looks drenched in carbon dioxide relative to water, alongside traces of CO, a little water ice, and dust, an odd balance compared with many homegrown comets. There are two broad ways to read that. Either it formed in a part of its original disk where carbon dioxide was easy to freeze and water less so, or it has been processed for eons by radiation and heat in a way that suppresses water's venting compared to CO2 and CO. Both interpretations are consistent with something ancient. The point for your viewer, we're not just watching an ice ball, we're reading a chemical time capsule from another sun's nursery. Now to the showy part, jets, tails, and the so-called fire hose. As 3i Atlas warms, pockets of gas trapped beneath a dusty crust burst through weak spots and spray into space. If a vent faces the sun, the jet can actually point sunward, which always looks counterintuitive on images, but is perfectly normal physics. The hottest face vents hardest, then sunlight and the solar wind bend much of that material away to shape the tail. Recent telescope images caught exactly this, a clear jet aimed toward the sun, extending for thousands of kilometers. Meanwhile, independent observations found water gushing at a rate that one team likened to a fire hose on full blast, even when 3i Atlas was still far enough out that water usually sleeps. Blend those two facts and you get a picture of a nucleus with active vents, likely rotating so the jets fan and corkscrew, feeding a coma that brightens as the sun's energy ramps up. It's dramatic, and it's also textbook comet behaviour, played in a foreign accent. That jet and tail choreography is more than eye candy, it's diagnostic. The distance a jet travels before dispersing hints at gas speed and dust grain sizes. The way the tail peels and kinks under the solar wind tells you about the electric and magnetic handshake between sunlight and the coma. If the nucleus tumbles, jets carve spirals and fans we can measure to back out spin rate and orientation. All of these clues feed back into the size and strength story. A tough, larger nucleus might keep coherent jets longer and shed bigger grains. A smaller, crumbly one may spray fine dust that creates a broader, softer glow. For an interstellar comet, every normal behaviour is still a revelation, proof that the basic thermodynamics of dirty ice hold up under alien chemistry. Then came the red planet cameo. Because Earth lost line of sight around the sun during the most tantalising weeks, Mars stole the best seats. In early October, 3i Atlas swept comparatively close to Mars, and Europe's ExoMars Trace Gas Orbiter managed to snag the comet as a faint, fuzzy moving dot, the nucleus wrapped in its coma, roughly tens of millions of kilometers away. Mars Express tried too. Its camera settings weren't ideal for something that dim and far, but the team still stacked images to hunt for a whisper of the visitor. That geometry mattered. With Earth hampered by glare, Mars-based vantage points were our only way to keep the thread unbroken as activity ramped up on approach to the sun. What could you learn from such a distant, modest dot? Plenty. Even a barely resolved smear tells you how fat the coma has grown by that date, whether the bright core is offset, a hint of jet direction, and how fast the whole envelope is brightening night to night. The Mars teams also pushed for spectra, fingerprints of gases in the coma, even if the comet was probably too faint for clean results at that range. It's a great beat for your viewers. Two orbiters built to stare at Mars turning just for a week into interstellar comet observatories. That opportunism is part of the new playbook. When a one-pass messenger like 3i Atlas roars through, every capable eye in the solar system pivots because the lab closes the moment it leaves the sun behind. If you want, I can now spin these sections into voiceover with pacing, slow build tension into the jet reveal, quick cuts for the Mars sequence, on-screen graphic beats, size estimate accordion animation that narrows as Hubble data arrives, and B-roll prompts tied to each claim. Picture the moment of closest approach as a paradox. The physics is at its most dramatic just when our view is at its worst. As 3i Atlas dives toward the sunlight that powers its show also blinds us to it. From Earth, the object is tucked in the glare, low at dawn or dusk, skimming the horizon, or even lost entirely in daylight sky where only coronagraphs and space-based instruments dare look. This is the phase when buried ices wake up, when fresh vents split open and gases roar out, when dust grains are lofted, sorted, and flung into the tail like confetti caught in a gale. Thermal stress climbs, hairline cracks can become fissures, weak crust can slump. Sometimes comets breeze through perihelion unchanged, sometimes they shed sheets of material, and sometimes they suffer dramatic outbursts, brief, explosive brightenings as a sealed pocket finally vents. The cruel part is that many of these signatures happen while the comet is too near the sun's disk for casual telescopes to track safely. Observers compensate with choreography, solar observatories that block the sun's face to reveal the faint halo around it, spacecraft at angles far from Earth's line of sight, ground-based teams ready to pounce the moment elongation improves by a few degrees. There's also a subtle piece of optics working in our favour. When dust sits at just the right Sun-Comet observer angle, it can brighten more than expected because it scatters light forward, like fog glowing around a car's headlights. That bonus glow can make a tail look suddenly richer right around the time it's hardest to see. A taunt and a promise in the same breath. If 3i Atlas was going to reveal its personality, this is where it would do it. The jet patterns, the colour of the dust, the balance between water and more volatile ices, the resilience or fragility of the nucleus. The lab doors are open, but only for a few feverish days in lousy lighting with the clock running. And then there's the realities of human eyes and backyard gear. Brightness isn't just what the comet is doing, it's also where it is and how we're positioned. Even an intrinsically lively comet can be a disappointment for the public if the geometry is poor. Too close to the sun in the sky, too far from Earth in distance, or venting in a way that produces more gas than dust. Gas glows nicely in spectra, but dust is what builds those dramatic, camera-friendly tails. For most casual observers under city skies, 3i Atlas was never going to be a blazing, naked-eye apparition hanging high at midnight. It's more the realm of determined amateurs with dark horizons, binoculars at the ready, and the patience to catch a faint smudge in twilight. That doesn't make the comet less good. It just means the best theatre was happening in wavelengths and instruments that don't fit in your backpack. Scientists prize signal over spectacle. A handful of clean spectra that pin down carbon dioxide or water can outweigh 1,000 pretty snapshots. A precisely measured light curve that shows how the comet's brightness responds to sunlight tells you about the grain sizes and the spin, even if the object never crosses the threshold of public wow. Managing expectations matters here. A rare interstellar visitor can be scientifically historic while being visually modest. If you keep the audience focused on the why, the chemistry, the origin story, the one-pass drama, they'll stay with you even if the sky never delivers a headline-grabbing streak. Comparisons help anchor that why. The first interstellar celebrity was a riddle wrapped in a shard. No obvious coma, a strange tumble, and a tiny non-gravitational nudge that sent modelers scrambling for natural explanations. The second was the opposite. All comet, all the time. Classic tail, classic gas. The comfort of something that behaved like the icy visitors we already knew, just stamped from away. 3i Atlas arrives as the third data point that turns a line into a trend. It leans cometward, more like the second than the first, yet it still speaks with an accent we don't hear from locals. That accent might be an unusual balance of volatiles, or the way activity wakes up farther from the sun than we expect, or jet patterns that suggest a crust unlike the dusty blankets we've mapped on familiar comets. Think of these three visitors as a spectrum rather than a category, from dry and puzzling through textbook and active to textbook but with quirks. With only two earlier examples, any new behaviour matters. If 3i Atlas shows that interstellar wanderers commonly carry certain ices in abundance, that nudges theories of planet formation beyond our own nursery. If its dust colours or grain sizes cluster with one of the earlier visitors, that hints at shared formation zones across different stars. And if its spin, jets, and outgassing look comfortingly normal, that's a result too. It says the physics of dirty ice behaves the same under alien chemistry as it does at home. The headline isn't just another one, it's "Now we can compare." Inevitably, the question bubbles up, what if it isn't natural? The speculation is part of the modern script. Some viewers want the tease, others the takedown. Here's the clean way to treat it. Start with the principle that extraordinary claims demand extraordinary evidence, then test the idea without sneer or bias. What would count as a genuine red flag? A perfectly smooth, engineered light curve without the flicker of jets or rotation? A path change too consistent, too sustained, and too clean to blame on venting gas? Spectral lines that don't match known ices, metals, or dust? Coherent radio transmissions from the direction of the nucleus, repeating on a schedule nature doesn't copy? If any of those appeared, the scientific community would pivot instantly, not to declare victory, but to design decisive follow-ups. In practice, the things we do see in cases like 3I Atlas tend to land on the natural side of the ledger. A fuzzy coma that waxes and wanes with sunlight, a tail that responds to the solar wind, gentle pushes that look exactly like jets switching on and off as the nucleus rotates. These are fingerprints, and they're hard to fake. Remind your audience that "we don't know yet" is not a dodge, it's a commitment to letting the data lead. Also, emphasize how falsifiable the natural hypothesis is. If the comet's behaviour refuses to line up with known ices and dust even after careful observation, the default story starts to wobble, and curiosity does the rest. Until then, the artifact angle is a narrative spice, not the meal. The real wonder is already staggering without gilding it, a fragment from a distant sun, flaring alive for a single swing past ours, leaving behind a trail of clues we can read for decades after it slips back into the dark. Chemistry is the language this traveller speaks, and light is our interpreter. Split the comet's glow with a prism, and you start seeing fingerprints, narrow signatures from gases lofted off the surface, broader swathes from sunlight reflecting off dust, faint hints of solids glowing in the infrared as they warm. For 3I Atlas, the question isn't just what's there, but where did this recipe come from? Different stars bake different planetary kitchens. If a comet forms beyond a certain freeze line in its birth disk, carbon dioxide can lock into ice as easily as water. If it forms closer in, water dominates while carbon monoxide and carbon dioxide act like shy guests, appearing only when the heat is just right. As 3I Atlas approaches the Sun, each ingredient takes its turn on stage. Carbon monoxide and carbon dioxide often start singing while the comet is still far out. Water follows closer in, and more complex organics trail behind as the crust weakens. By watching which lines brighten first, which plateau, and which refuse to appear at all, we sketch a rough map of the comet's childhood neighbourhood, hot or cold, calm or UV blasted, rich in carbon or oxygen, dust-choked or pristine. Dust tells its own story. Size matters. Big grains scatter light differently than fine powder, and polarimetry. The way light's orientation changes after bouncing off the dust acts like a micrometer at astronomical distance. Coarser grains suggest tougher crust or gentler outgassing. Ultra-fine fluff hints at fragile surface layers that crumble under modest warmth. Colour helps too. A slightly red dust continuum can mean space-weathered organics, irradiated for epochs between the stars. A flatter slope leans toward fresher, more reflective grains. Mix in temperature readings from infrared observations, and you start separating rock-like silicates from darker, carbon-rich material. Even the way the dust fades after a burst reveals stickiness. Do grains clump and fall back, or do they sail free? Every one of these clues carries an accent from another solar system. Isotopes are the quiet bombshells. We don't need equations here. just the idea that some atoms come in heavier and lighter versions, and the relative mix can tag the conditions under which ice is formed. Ratios in water and carbon compounds can hint at whether 3I Atlas condensed in a chilly outer disk or a somewhat warmer midzone. Metals drifting in the gas, like sodium that flares at certain distances from the sun, or trace atoms liberated from dust by sunlight, can refine the picture further. Are we looking at a nucleus with pockets of extremely volatile ices sequestered under a desiccated rind, or a more uniform interior that exhales steadily? If the spectral playlist changes with rotation, lines brightening as a particular patch faces the sun, then we can tie chemistry to geography and start mapping the surface in themes. A carbon-rich cap here, a water-heavy plain there, a stubborn, inactive plateau that keeps its secrets no matter how hard the sun stares. The most delicious part is time. Chemistry isn't static, it's choreography. A week before closest approach, carbon dioxide might lead. Days later, water surges. An hour after a flare, a suite of organics peeks out, only to retreat as vents choke with dust. If 3I Atlas carries complex molecules, alcohols, simple sugars, ring compounds, those are breadcrumbs from prebiotic chemistry in another stellar nursery. No one observation gives you the story. The story emerges from the rise and fall of many lines stitched together. That is why campaigns matter. A deep spectrum taken too early can miss the water. One taken too late can miss the carbon monoxide. The full arc, quiet approach, fevered middle, cooling exit, reads like a chemical diary written in the hand of a different sun. All that chemistry matters even if the nucleus decides to shed its skin. Fragmentation is the cliffhanger everyone waits for with a sun-glazing comet, and 3I Atlas arrived with all the right tensions. Imagine a walnut made of puffed snow, peppered with pebbles laced with trapped gases. As sunlight digs in, heat travels slowly. Surfaces scorch while interiors lag behind. That mismatch breeds stress. Meanwhile, jets act like many tiny thrusters, spinning the nucleus faster or tugging unevenly on weak seams. A sealed pocket opens and the local pressure plummets. Another pocket swells and the crust above it domes like a blister. Sometimes a slab peels away and sails off. Sometimes the nucleus cracks cleanly into pieces. Sometimes it just sheds a steady sleet of crumbs. The signs are subtle at first. A sudden jump in brightness, a tail that forks, a central condensation that looks stretched rather than point sharp. Then come the giveaways. Multiple beads in the core, each with its own miniature coma, a cloud of fresh, fine dust that makes the whole scene look soft, like breath on cold glass. A harmless interstellar visitor can still sharpen our survival instincts. Treat 3I Atlas as a live-fire drill for planetary defense, not because it threatens us, but because it stresses every step in our response chain. Detection is first. Fast movers on steep, odd angles challenge survey software that was trained on more leisurely, homegrown traffic. When a dot slips across the CCD much faster than usual, it can be mistaken for noise, a satellite glint, or a streak that the pipeline auto-rejects. Catching 3I Atlas forces teams to tune those filters, relax the rejection thresholds without opening the floodgates to junk, and build fast mover branches that flag candidates for humans within minutes, not days. Next comes astrometry, the painstaking measurement of position. With unbound visitors, the window to nail down a path is brutally short. Each hour of delay fattens the uncertainty cloud. This is where a global, redundant network pays off. Amateur and professional scopes in staggered longitudes hand the baton around the planet, filling in the track while others sleep or sit under clouds. The better the track, the quicker you can answer the first public safety question honestly. Is it coming anywhere near Earth? Even when the answer is no, the discipline of answering fast matters, because rumour outruns nuance. Then come the follow-ups that simulate the next class of true hazards. Can you pivot giant telescopes on short notice when a target of opportunity request pings in at 3 a.m? Can you preempt lower priority programs without sparking turf wars? How quickly can spectroscopy teams lock down the venting gases so dynamic modelers can estimate non-gravitational pushes? Those tiny pushes, jets acting like microthrusters, are exactly the kind of physics that, when mismodelled, makes trajectories drift and miss by millions of kilometres after a few weeks. In a real Earth-crosser scenario, that's the difference between no risk and we need to keep watching. Radar won't save you for a dim, distant object like 3i Atlas, but rehearsing how you'd cue radar, who would lead, and how you'd share the data is still valuable. The exercise extends to communications, a clear, single page that lists what we know, what we don't, and when we'll know more, lowers the temperature online and frees scientists to work instead of firefighting speculation. And there are hardware lessons too. Encounters like this are reality checks for Park and Pounce mission concepts. Small spacecraft staged in convenient orbits, designed to sprint toward whatever wanders in. Even if we don't launch during 3i Atlas, its appearance puts pressure on timelines, on propulsion trade-offs, and on the nimbleness of mission approvals. A drill is only as good as the debrief. After this visitor fades, the right move is a candid after-action report, which alerts came too slowly, which telescopes were overbooked, where codes crashed, where human bottlenecks formed, and which parts of the public message muddied rather than clarified. When the next unknown shows up, and one will, the difference between scramble and choreography will have been decided by how seriously we took this rehearsal. The statistics piece sounds dry, but it's where humility meets math. Before the first outsider ever appeared, most of us lived with a vague intuition. Surely there are fragments between stars, but spotting one felt like winning a cosmic lottery. Once we had the first and then the second, the conversation changed from if to how often. 3i Atlas pushes that update further. The rate you should expect to see visitors is not a single magic number. It's a moving target tied to how hard and how cleverly you look. Survey depth, sky coverage, cadence, and the ability to notice faint fuzz instead of just point-like dots. All of these act like knobs on a radio, tuning in more or fewer detections. Turn the knobs far enough, and what felt rare at the eyepiece becomes routine on the server log. That doesn't make the universe less wondrous, it corrects our sampling bias. We were fish who only counted what swam through our net, then declared the ocean mostly empty. Build a bigger net and the ocean reveals itself, but even with better nets, selection tricks lurk. We're predisposed to meet the loudmouths first, the dusty, active visitors that flare and shout with long tails. Quiet travellers with little dust, odd colours, or smaller sizes could skate through our datasets under the detection threshold. That means our first few examples, 3i Atlas included, might paint a skewed picture of the true population. The remedy is to keep two ledgers in your head. The observed sample, with all its biases, and the inferred population, which tries to correct for what you're missing. As detections accumulate, the gap between those ledgers narrows and your priors, your honest before-the-fact expectations get sharper. This is where surprise evolves. The first detection shocked us. The second taught us to expect more. The third begins to set a pace. At some point, an interstellar comet stops being a black swan and becomes a grey swan, rare in the grand scheme, expected in the surveillance regime. The real surprises, then, migrate from the mere fact of arrival to the specifics, a chemistry that doesn't fit known formation zones, an activity profile that wakes up absurdly far from the sun, a spin that suggests a strange internal structure. That's healthy. In science, you want surprise to move from "we saw anything at all" to "we saw this particular interesting deviation." It's a sign your priors are maturing. There's also a social dimension to the numbers. Rates become budgets. If we think we'll see one interstellar visitor every few years, That justifies maintaining a rapid response observing program year in, year out, instead of scrambling only when the siren blares. It affects training. You can't keep a global community sharp on pure theory. You need real reps. It even shapes careers. Graduate students choose projects they believe will actually get data before they graduate. And for your audience, the statistical story keeps hype in check while preserving awe. You can say, truthfully, this is rare enough to be special, but common enough that we're building tools to catch the next one better. That balance, special but not miraculous, earns trust. And then there's the culture machine we live in. The headlines, the hot takes, the meme economy. A visitor like 3i Atlas is a perfect specimen for the internet. Mysterious, photogenic in expert hands, and resistant to simple answers during the very period when attention is highest. That's volatile fuel. If you're telling this story to a wide audience, you get to choose whether you're a flamethrower or a lantern. A flamethrower leans on the spikiest possibilities and upgrades the unknown into the sensational. A lantern makes the unknown the hero. One practical way to be a lantern is to set a rhythm in your narrative. Every time you showcase a dramatic image or provocative claim, follow it with a calm, specific, here's what we know, here's what we don't, here's what would change our minds. Make that cadence predictable, and you'll feel your viewers relax. They'll trust you to handle the tension without trickery. Another useful move is to separate wonder from certainty on screen. 2 boxes side by side, established, and hypotheses under test. Watching items migrate between boxes over the weeks is more satisfying than any one-off bombshell, because it models how knowledge actually grows. Memes thrive on crisp symbols, so give them good ones. Instead of letting alien tech dominate the discourse by default, offer equally sticky frames. Postcard from another sun, One Lap Laboratory, Messenger not a menace. Those phrases do real work. They steer curiosity away from fear and toward participation. Invite your audience into the process. Show them how volunteers and small observatories contribute crucial follow-ups, how a well-timed amateur image can tighten an orbit solution, how data goes from raw smudges to physical insight. People share what they helped build. If you give them the feeling of co-authorship, we caught this together, the meme that spreads will be one of collective discovery, not conspiracy. Finally, respect the half-life of attention. The most breathless phase, perihelion in the glare, is precisely when answers are scarcest. Promise updates on a schedule rather than dangling soon. When new data arrives, foreground what changed rather than rehashing everything. Admit when an earlier hunch didn't pan out. Model intellectual honesty as a plot twist, not a humiliation. And when 3i Atlas fades into the dark and the trending bar moves on, close the loop. Make a short epilogue that summarizes what stuck, what fizzled, and what questions now stand in line for the next visitor to answer. That ending matters. It teaches your audience that the arc of a mystery doesn't collapse into a single reveal. It resolves into a better question. If you do that, the story of 3i Atlas won't be just a spike on a graph. It will be part of a culture that learns to love the long game, patient, evidence-first wonder in a world built for scrolls and scrolls of instant gratification. As 3i Atlas slips past the sun and begins the long climb back into the dark, the tempo changes from spectacle to forensics. The coma shrinks, the jets quiet, and the bright, messy halo that made everything hard to interpret begins to thin into something more transparent. That's when careful light curves matter most, night after night of steady photometry to watch the brightness taper, not as a graceful fade but as a set of steps and plateaus that betray which vents are still sputtering and which have gone dark. Spectra too tell a different story on the outbound leg. Close to the sun, the hottest, easiest to evaporate ices speak the loudest. Farther out, as the heat fades, you hear the deeper notes, slower chemistry, heavier grains that linger, faint hints of leftover gases that weren't dominant before. If a new fracture opened at perihelion, you might see a late second wind as sunlight reaches a fresh pocket that was sealed during the inbound run. If the crust held, you'll see a cleaner, quicker shutoff. Either way, the shape of the fade is a fingerprint. The tail evolves from banner to breadcrumb trail. Early on, radiation pressure and the solar wind peel the dust into a wide, bright fan. Later, the big grains, the ones thrown out with less speed, lag behind and stretch into a narrow, faint ribbon you can only catch with long exposures and careful stacking. That ribbon is priceless. Grain sizes, ejection speeds, and the timing of the strongest outbursts are all encoded in its geometry. Polarization measurements, if observers can wring them from the dimming glow, add texture, literally, by hinting at whether the grains are fluffy clumps or compact shards. Meanwhile, the nucleus itself keeps its secrets, but loosens its grip just enough to measure. Subtle wobbles in the light curve can reveal spin rate changes caused by the jets acting like tiny thrusters at perihelion. A small spin up or spin down tells you the jets weren't evenly spread. A steady spin suggests either symmetry or a short, violent vent that cancelled itself out over a full rotation. Trajectory work continues in the background like a drum beat. With the jets waning, the path settles toward a clean, gravity-only arc again, and that lets orbit calculators separate what the sun did from what the vents did. The result is a before and after map. Here's the incoming approach, here's the outgoing escape, and here's how much the comet's own breath nudged the difference. On rare occasions, a comet will even display tail disconnection events, where the magnetic handshake between the solar wind and the comet snaps and reconnects, slicing the tail like a ribbon in a gust. Catching one on the outbound leg would give space weather scientists a bonus dataset they rarely get from an interstellar visitor. All of this is patient work, unglamorous compared to the inbound fireworks, but it's where the long-term value lives, the part you can compare, line by line, with the next visitor and the one after that. There's a housekeeping side to the long exit that matters more than it sounds. Observers scour their archives for pre-discovery images that might have caught 3i Atlas as a faint smudge months earlier. Every extra point on the timeline shrinks uncertainties and strengthens everything else. Teams merge datasets, big telescopes, small telescopes, spacecraft vantage points, into a single public record so that future researchers can test new ideas without rebuilding the world from scratch. And theorists go to work on the inversion problem. Given the dust we saw and the way it moved, what surface patterns could have produced it? That means putting imagined vent maps on an imagined spinning shape and asking which maps recreate the real sky. You won't land on a single, true answer, but you'll carve away the impossible and keep the plausible. The farther 3i Atlas recedes, the more this becomes the story. Less chasing a moving target, more extracting a biography from fading traces. In a few months, the comet will be too faint for all but the most determined observers. In a few years, even those will let go. What remains is the record. A frozen, multi-wavelength portrait of a traveller we met once and will never meet again. So, does this traveller deserve the dramatic label that brought us here? The Black Swan test isn't about vibes, it's about priors, impact, and hindsight. On the first count rarity, our expectations have matured. Before the age of all sky, high-cadence surveys, an interstellar visitor felt like a myth you told at star parties. After the first, odds shifted. After the second, we began to budget time and attention for the next. With 3i Atlas, the third, rarity is still real in a cosmic sense, but in a practical observer's sense, our surprise should now be tempered. It's getting harder to call the appearance itself unforeseeable. On the second count, impact, the case is stronger. Even if no city ever notices it in the sky, the ripple through science is non-trivial. new constraints on how other suns build and eject debris, new lessons in how to coordinate global follow-ups, new pressure on rapid response mission concepts, and a clearer blueprint for how to extract maximum knowledge from a one-pass messenger. That's genuine systemic impact, less cinematic than a dinosaur killer, but exactly the kind of jolt that rebalances budgets, schedules, and theories. The final count is the hindsight trap. Watch how quickly tidy explanations bloom after the data roll in. Of course we saw this now, people will say. Given our survey depth and the number of ejected planetesimals in the galaxy, it was due. Perhaps. But did we stake that claim publicly and precisely before discovery, with numbers and timelines that could be wrong? Or are we retrofitting confidence to match the outcome? The honest answer probably lands in the middle. Specialists did predict we'd start seeing more visitors. Few pinned down the exact cadence. That ambiguity is why the fairest verdict may be to downgrade the label. 3i Atlas looks less like a black swan, an event that humiliates our expectations, and more like a rare bird we had learned to expect in the new season. A grey swan, still impressive, still rare, but now inside the envelope of what a well-instrumented civilization should be ready to catch. That doesn't make it smaller, it makes us better witnesses. There's also a human coda to the verdict. The true impact of 3i Atlas may be cultural, the way it trains millions of eyes on the patient craft of science without requiring catastrophe to hold their attention. It demonstrates that wonder survives even when hype is managed, that a story can be told with clean boundaries between what we know and what we're testing, and that we changed our minds because the data changed is not a weakness but a rhythm. If that sticks, the rare visitor will have altered not just models of distant dust, but habits of thought closer to home. And when the glow finally dims beyond reach, here's the way to close the book. We met a messenger from another sun, alive for a single lap through our light. We watched 3i Atlas wake as it fell inward. Quiet gases whispering first, then a rush of jets, dust fanning into a tail, and the brief blinding thrill of perihelion. We argued, we measured, we coordinated across oceans and orbits, and then we followed the traveller out as the noise receded and the signal grew clear. In the end, the verdict we reached says as much about us as it does about the comet. We're a species learning to live with rare things by preparing for them, to separate awe from alarm, and to turn every unexpected arrival into a lesson we can keep. If this story did its job, you won't walk outside expecting a sky-wide spectacle tonight. You'll look up and think about how many worlds have made and lost fragments like this one, how many postcards are drifting between the stars at this very moment, and how often we now catch them. Somewhere out there, another traveller is already inbound, dimmer than a whisper, brightening with every hour. When it arrives, we'll be better listeners because 3i Atlas taught us the tune.